Hello, good morning. This is welcome for our webinar of the day, leveraging serverless cloud to improve business agility. We'll just give another minute and we'll get started. Please stand by. Hello, welcome again. Good morning, everyone. We have great attendees today. Great number of people joined us. Thank you for joining. Today's webinar is about serverless computing, how we can leverage serverless computing to improve business agility. So just as everyone are impacted and experiencing, Corona pandemic has turned business and communities upside down and sideways front. Businesses are challenged today with the need to pivot their directions, change operational modes very fast, and operating models and strategies on a very short notices and a very short timeline. We'll see how serverless computing can especially help businesses gain that agility and faster reaction times as they are struggling with this particular pandemic. Our webinar will be about 45 minutes to 50 minutes, for 10 minutes for questions. If you have any questions, you can certainly type them in the questions box on your right on the GoToMeeting panel, and we will answer them towards the end of the presentations. Introductions first. I'm Chala Palaniappan, VP of Client Services, and my co-presenter is Vijendra. Vijendra, do you want to say hello?
Hi everyone, I'm Vijendra, and I head the Cloud and Mobility practice at Trigent.
Great. A quick introduction to Trigent. We are a 25-year-old consulting, software development, and testing services company. We provide services to US clients mostly. Our head office is in Southborough, Massachusetts, and with multiple development centers in India. We cover a wide range of technologies across cloud, mobile, and data sciences. We are a Microsoft Gold partner and Azure AWS consulting partner. We work mostly in these domains, which are insurance, healthcare, transportation, logistics, manufacturing, and lastly, high technology. High tech, we mean mostly other software providers providing software in the software as a service model to a variety of industries. So what can serverless do for you? In our thinking, serverless architecture, because of its very low engineering lead time, can bring a lot of agility to the businesses. Traditional architectures have large responsibilities that are beyond our applications, such as you need to maintain infrastructure, you need to maintain various other configurations, scaffolding that is needed because your application needs to depends on them. All that is taken off in the serverless architecture. So you focus only on your application logic, nothing more. So serverless computing abstracts the cloud infrastructure even further from the developers to provide that kind of a fast engineering lead time to bring agility into their application development. Let's look at what a successful scaled agile software development looks like. We have traditionally used the term disruption in the last 10 years or so primarily to mean innovation. But COVID really has taught us what disruption is, right? Business have been disrupted really badly. Business as usual has become business as unusual. So in our thinking, business agility is the ability to reconfigure strategy, structure, process, organization, and also architecture to our architecture. When I mean architecture, technology to value creating and value protecting opportunities that are essential for the businesses. So in that sense, processes such as Agile, Scrum, CI/CD all provide us that scale or the rapid delivery, quick turnaround that provides that. So the processes are there. Organizations have gone very different. Large teams are no longer the norm. Smaller autonomous teams are more preferred, typically 6 to 8 people. Jeff Bezos popularized the term by 2 pizza teams. Essentially, the idea is that you need to have a technology team that can be just fed by just 2 pizzas, about 6 to 8 people, right? But the legacy methodologies, traditional methodologies, waterfall, they don't support this kind of agility. Neither do these legacy architectures. Legacy architectures don't support the agility or the scale. So if without the architectural innovations, you really can't have agility. And let's look at architectural evolution in the last 10 years or so, or 15 years or so. So this is very familiar to many of us. It's a familiar 3-tier architecture. It's been around since middle of 2000s. Essentially a presentation tier, business tier, and data tier. The presentation tier is largely in the mid 2000s supported by Java Server Pages, ASP Pages. Business tier is largely managed by EJB or .NET, and you had your SQL Server, Oracle, other traditional relational databases on the back end. The same thing is possible. This is even possible today in 2020 with certain number of changes. You can still do React.js on the presentation tier, Node.js in the middle tier, and a highly scalable Cassandra-like cloud database on the back end to do scale. What are the strengths? These are these are still as popular. Popular in the sense they can still suffice to a lot of application needs. They provide a rich front-end frameworks, scalable. Middle tier by itself is scalable, and the databases can be highly scalable with databases like a Cassandra and everything else. But the problem is that the middle tier causes a lot of problem in its stateful manner, and we can kind of address that in some way. Certain ways, right? The weakness is the stateful middle tier. So we'll address that in a different way, how this can be changed. So one aspect of how to scale that is typically what is known as a sharded architecture. By this, scaling vertically servers with more memory, storage, and processing power does work for a while, but eventually it's going to hit a limit. So you need to scale horizontally. So the scaling horizontally happens by introducing a router, first of all, right? So we use a router load balancer that intelligently distributes the load across many different instances, multiple instances. So you can take the same application and run the same application instance multiple times, and you have a horizontal scalability. When the volume of data increases impacts that, we can also apply a certain amount of data separation, right? So you can separate your application along the data lines And you can say, for example, you can separate your application based on a tenant ID, for example, or a geographical region where it is coming from, and only from users from particular geography can go to a particular instance, or it could be any other thing that makes sense for your business. So essentially, your database can be split across some organizational boundaries, and you can provide that. And this is also largely used by SaaS providers to some extent, where the clients need a data isolation, right? Some of the clients said, no, I want my data to be maintained in only a specific database that is isolated from others. The SaaS providers are able to do that. Or if any governmental regulation, such as like GDPR or any other stuff, says like, okay, any European traffic comes from there, need to be maintained only in servers or anything in the data servers in the European state, that is possible. So all these things are possible within the sharded architecture. So also it is very, very easy for certain type of application. For example, applications such as Slack uses this architecture because it is very easy in the Slack, because every channel typically resides in a very, very isolated way. But the weakness is that there is no comprehensive data view, and oversized sharded can be very, very difficult to manage. So we need to manage that. So one way to handle the oversized sharded, where essentially providing kind of a read-write replication and a master-slave kind of architecture to manage the sharding to some extent. But all these things are able to scale to only to some extent. So let's look at scalability in a different way for a second, right? So what we understand scalability through what is known as a scale cube. Typical x-axis scaling is characterized by horizontal duplication. We run multiple copies of the same application behind a load server, right? Z-axis, we run multiple copies of databases separated through some kind of a primary key, customer ID, tenant ID, or all the other those things. So we provide a data separation, and we scale it, splitting the similar things, right? Lastly, the y-axis scaling is a functional decomposition. This essentially allows us to break up the application in by smaller application and services. We no longer take the huge application and bundle all that into one application, but we try to break the application by functional decomposition of separate services, functions, or smaller modules. That brings us to microservices. The microservices, I don't want to go into the definition and a lot of explanation. There's a very, very apt definition by Martin Fowler. I think everybody can understand this very well. The key things are independently deployable services, services that can be independently deployed, scaled. Also, automated deployment and decentralized control of language and data. Essentially, each services can be managed and controlled by different teams that have their own choice of language and data. So let's look at microservices a little more into what kind of characteristics or benefits it provides. One of the biggest things is the separation of concern. The software should be separated based on the kinds of work it does, right? Meaning, like, essentially it is dependent on the kind of work that the software does. You can encapsulate it differently. Different parts of the application should use encapsulation to insulate them from other parts of application. So one part of application can be taken down, redeployed, or if that application or that particular service fails, only that is impacted. Rest of the application can still continue to run. Netflix is a great example of microservices. In late 2000s, Netflix moved from monolithic to microservices architecture, and the developers were able to deploy thousands of lines of code, millions of lines of code to their large multi-millions of subscribers across the world. Spotify, Uber, all of these highly scaled organizations or applications all of them use microservices. Also, because of the services are small, the virtualizations becomes easy. Smaller code bases also means quicker deployments, quicker rollouts, and when the services are also separate, we can scale more easily only the services that need scaling rather than scaling the entire application. If you have to scale the entire application, that takes a lot more effort than scaling a specific service or specific module. So that elasticity is highly improved in the microservices architecture. Lastly, each team could decide on their own choice of technology, programming, or any of those kind of things that they provide, so which they are good at. So let's look at a kind of a comparison of a monolithic to a microservices architecture just to understand. Let's consider an example of a web commerce, e-commerce application. We have a very great graphically rich UI with a lot of graphic images, like essentially product images or any of those kind of things. Engaging UI, primarily done in HTML, CSS, images, all that stuff there. We need some way to authenticate buyers. So you have an authentication module and a catalog or order modules, and a final reviews module allows people to write product reviews, buy products, and things like that. Very similar to Amazon or any other e-commerce, right? And all our persistent data is stored into a single database, relational or otherwise, but a single database. Moving this to a microservices architecture, what we do is the first thing is the storefront UI is moved largely out into a static services such as S3 or something like that. So a lot of images are now no longer served through your application, but delegated to other services such as the cloud services such as S3 or something like that. We introduce an API gateway to marshal the traffic, so that the API gateway is introduced. We split the database along the functional lines, and also we split each of the module into a service itself. So that's easy. But some of the other differences that in the monolithic application, we had to deploy the whole application as a single WAR file or a jar file or whatever it is, and everything was done by a single release pipeline. It's very highly rigid to scale. It also is highly impactful changes. A particular module change in a particular module could impact other modules. It's also difficult to adapt or move into newer technologies. But in the microservices, deployments can be independent. Each service can be deployed independently. Changes are isolated from impacting other parts of the application, and also the choice of technology can be made by the teams in a smaller scale rather than across the organization. Let's look at the advantage and drawbacks of the microservices. The biggest thing is the polyglot programming. We can choose our own language. So each services can be written differently. You could have a service that is written in PHP, another service written in Java, another service written in Python, whatever that kid choice of maybe. Each service is also very well isolated by logic and technology so that they don't impact others. Services are small, so you can build and deploy faster iterations. But the difficulties are, the drawbacks of the difficulties are different, which is that complex, it's very complex. Complexity is introduced because that we are separating these things. So there's need to be some kind of a orchestration or a choreography between each of these things. And it also becomes a little bit difficult to debug and test. How do you test a distributed system? Distributed systems are always very difficult to test and certify. Partial failures are difficult to handle, meaning you need to have a cleanup logic across many different places. And lastly, operational overhead are increased because every service needs to have a logs, health check, and those kind of things, rather than a centralized provision that allows the entire application to be operationally managed. So to some extent, from here, how do we move into the serverless architecture, right? What does the serverless architecture differ from microservices architecture? So one of the big things is that, as we've seen, the storefront UI still is in an S3 bucket kind of a thing, which is from a service, which is great. Now we also isolated the authentication logic in the original application is now replaced with a third-party backend as a service or a PaaS kind of a module, which is in, let's say, for example, Cognito or Auth0. In a monolithic architecture, all flow, control, and security was managed by a central server application, but there's no central arbiter of the concerns. Instead, we prefer choreography over orchestration. With each component kind of playing more architecturally aware role. Each function does more by itself. This allows the backend server code without managing your own server system or your own long-lived server application. Right? There is no long-lived server application. Each of them is broken down into function and how these functions are able to run by themselves and manage it. The API gateway is still a similar kind of API gateway, but a little bit of intelligence is introduced there. The API gateway can receive the request. It is more of a configuration driven. A lot of configuration can be there as to what request gets routed to what functions and how to marshal them. And the HTTP parameters that is coming in may be transferred into a more request parameters for the actual functions itself. So it does a little bit more intelligence as like now rather than just passing the parameter, even though you can just pass the URL parameters, but it can also be translated to JSON object and passed to a specific function. API gateway can also perform certain number of authentication, input validation, code mapping, and other stuff. So you got a much better API gateway. Typically, these are provided by your provider themselves, and each of the functions are running in a short-lived environment, which is not a container, which is not a cloud server, but it is managed completely by your cloud provider. So this provides you a very high-level overview or a visual representation of the serverless architecture. But to dive deeper into the serverless architecture and get into very many different types of deployments or uses and how the architecture differs from different kind of applications, I'll let Vijendra take over from here and talk. Vijendra, over to you.
Thanks, Chala. Let me share my screen.
Great.
All right. So till now, Chala has explained the evolution of serverless architecture, starting from monolith, three-tier sharded architecture, microservices, etc. Now, let us deep dive more into the serverless architecture. Serverless architecture is the next evolution of cloud nirvana. It's a major milestone in the cloud computing area. When I say serverless, it doesn't mean that there are no servers involved. There would be servers, but managed by the cloud service providers. Since the servers are managed by cloud service providers, we can concentrate on our application building and then running those applications. Since the cloud service providers manage the whole infrastructure, they will manage, when they say infrastructure, they manage servers hardware, and then any OS or runtime patching, health-related checking, and then monitoring the things, scaling policies like how it has to scale when the spike goes, when the load goes up, and then the capacity planning, and then the availability zone mapping. All such things will be managed by the cloud service providers. So complete operational responsibilities are held by the cloud service providers. It all started when AWS, the Amazon introduced the Lambda functions in the year 2015. So now we know the serverless, what it is. Let us see how it is different from other service models. We have heard about platform as a service, infrastructure as a service, and then also a software as a service. How serverless is different from all other things. This chart depicts the difference between all the things. You can see that in on-premise, we had to maintain all the things, so starting from networking, storage, servers, virtualization, OS, middleware, runtime, data, and then the framework, applications. Everything has to be managed by on our own when the application is on the premises. In the infrastructure as a service IaaS model, till virtualization, service provider will manage. The rest, operating system and other things, have to be managed by us. In the place of platform as a service, till runtime, everything is managed. Only the frameworks and then the applications have to be managed by us. They'll give control only to these. But in case of serverless architecture, only the applications have to be managed by us. The rest, including the server, networking, everything is managed by the service providers. But a SaaS product, software as a service, is completely different. Everything is managed by the service providers. We have to utilize only the applications directly. Even the applications are managed by the vendor there. You must have observed even the other thing here. The moment we go from SaaS to the on-premise, there is a increased control of the customization. In the SaaS model, we don't have any control on the product at all. We don't have any control on the server, anything. The provider will provide all the things, and then we just have to make use of it. There is no control on it. And even the customization is very, very limited. The moment we go on the left side, we get more control on everything. On the on-premise level, we get control of whole thing, including the networking level to the application level. All complete stack we have to control. On the same side, if you go from left to right, the complexity will be reduced. Here on the on-premise, the complexity is more. We have to take care of everything. That's the reason it's more complex. And then when we move along on the right side, it's very, very less. The complexity on our side is very, very less. This is another chart. It depicts the difference between the PaaS and serverless. We have put this slide mainly because a lot of people are specifically asked this question in our previous sessions, like what is the difference between PaaS and serverless. In the PaaS, we have got more control over the deployment environment, but in the serverless, it's less control on the deployment environment, and then application has to be configured to scale automatically in the PaaS environment. Here in the serverless, application scales automatically, service provider takes care of it. Here on the PaaS level, application takes a while to spin up, and here on the serverless, application code only executes when invoked. On the PaaS, whether you're using the service at that moment or not, finally there is a fixed cost even if they're not in use, but serverless, only when it is in use, you'll be charged. In both the cases, you have to write the code, and also there is no server management. So what are the different advantages with the serverless architecture? Mainly in the serverless architecture, there is no need of running a server all the time 24/7. That means only it removes the need of any server which has to be always on level. That we generally do that in the on-premise level. We pay only for the usage of that server or the computing time. When it is used for 5 minutes, only for 5 minutes will be charged. It's more like a operational expenditure we have to incur, not the capital expenditure. When you go with the capital expenditure, obviously cost will be more. In case of operational expenditure, cost is very less. Also, very minimal level of maintenance work is involved with the serverless. The main reason is we don't need to deal with anything with the infrastructure. It's only our level, application level maintenance we have to take care. One additional feature, important feature, is that automatic scaling. Service provider takes care of scaling it up when the load goes very high. So when the usage goes high, automatically it scales up and then provide many instances in the backend so that we get the scalability aspect automatically. We don't need to really provision anything to do with the scaling aspect. Similar to that, it's also provides the high availability environment. When the server goes down, we don't need to worry. That means in the regular environment, when the server goes down, we have to take care like fault tolerance level. If the server goes down, we have to bring the other server, and then we have to make adjustment to all those. In case of serverless, service provider will take care of it automatically. We don't need to check whether it will be available or not. They ensure that all the time it is available 24/7. One more point is faster time to market. Since underlying logic, we don't need to worry about it. It's also it provides a very easy way of deployment, and then the release times, it's very fast for pushing our application to the market. Since we don't need to deal with any other infrastructure, etc., we can concentrate more on our application and then innovating it, so that increases the agility. Main important, most of all these is it's supported by all the major public cloud providers. That includes Amazon Web Services, AWS, Microsoft Azure, and also the Google Cloud Platform. Let us go in depth about serverless architecture. What are the different components of serverless architecture? Predominantly, we have two components. One is function as a service, and then the backend as a service. Function is nothing but in a regular way in the programming world, when we have the habit of creating a function for achieving any task, we can assume it's very much similar to that. So we have got set of code lines which can be executed in a container level. Cloud provider will take care of executing that and then giving us the result. So it's PaaS is we can define it as a fully managed stateless compute containers to run the custom code which we write, and it is supported by all programming languages: Java, JavaScript, PowerShell, Node.js, C#. Yeah, most of the programming languages are supported by the cloud providers. PaaS, to give an example of the PaaS, Amazon in world, they call it as a Lambda, and in the Azure cloud provider, they call it as a function. Similar to that in the GCP, Google Cloud Platform, they call it as a function. That's all about the function as a service, or PaaS. The backend as a service is the services, automated services, which are excluding this PaaS, is nothing but BaaS, backend as a service. So it's called automated and managed backend services for web and mobile applications. These days, since mobility predominantly taking over all the enterprises, we have to use backend services for all the mobile applications. And that's the reason many people call even BaaS as MBaaS, that is mobile backend as a service. To give an example of the BaaS, that includes database management and user authentication services, notification services, storage services, etc. Mainly, the serverless architecture uses the event-driven patterns. It's a stateless, event-driven pattern. Most of the times we use in the serverless architecture. On the left side, you can see the event source is the one which triggers the functions to execute, and then the functions, when they execute, they can take the help of any backend services. In the event source, you can see that simple queuing service or SNS, simple notification service, or API gateway. These are, by the way, in all our slides, we have used AWS components just to make it like a simple. Of course, even the other cloud providers have got equivalent services on their own. They're named in a different way, but the functionality would be almost same. So whenever there is any event happens, to give an example, there is a request comes to the API gateway. There is an API request comes from either mobile application or from the web. That triggers Lambda function, and finally that gets executed by making use of backend services and gives back the result. Similarly, whenever any item comes to whenever an item gets pushed to the queuing service, then it will be triggered and then get executed. Some of the event trigger services we have listed in this slide. To give you an example, data related services are called S3, mainly for using for storing any kinds of files or the objects. DynamoDB is like a NoSQL database. You can find out the details on the internet. There are plenty of documentation available to for all these on the Amazon website. So when I say execution models, there are multiple ways of using, though it is called event-driven, it's event-driven can be used in 3 different ways. One is using the synchronous way, other one is the asynchronous way, and then the polling way. In the synchronous way, most of the times it's like a push. We have got some kind of API which is invoked by a application. It can be a web or mobile application. When it gets called, it will be pushed to the Lambda function that will get triggered and then executed. Results will be sent back. In case of event, asynchronous level, somebody in the sense any application can write a file to a S3 location, or there can be any notifications into the SNS service. At that time, Amazon will take care of creating a asynchronous request to call the Lambda function. One more way of using this is the polling mechanism. Lambda function can be configured to poll the backend database or a Amazon Kinesis service. So whenever there is any change, we keep polling. We can find out that there is a change, and then based on that, we execute the Lambda function. These are the different execution models provided by Amazon Lambda. So what are the different factors to be considered for our development work? Mainly, we should analyze the system, analyze our application for number of requests in the application, and then the cost factors. To give an example, when I explained about the Lambda function, it generally they charge based on the time it is executed. So that means if too many number of requests goes to the service, obviously the cost will go up. Definitely the serverless Lambda functions are very good if number of requests are very less. If we go with too much of volume, then the cost will also go up. So that we have to take care before we jump on implementing the serverless architecture. Next point is processing time required by applications. Some of the applications, when I execute to perform any operation, it doesn't take much time, probably 2 minutes or maximum 5 minutes. And there are few applications which require a lot of CPU time that should be continuously running for at least 45 minutes, even in this era. Just because it contains a lot of business logic, and then to come up with some kind of output, it requires CPU to be utilized at least for half an hour to 1 hour level. So there is a problem with, there is a limitation with most of the service providers that serverless functions are limited with some kind of time. To give an example, Amazon Lambda has got 15 minutes processing time. There is a limit on that. If the code extends that 15 minutes time, then it will kill that whole process, and then you will not get the result. So your application, you have to analyze your system or the application to find out how much time it takes, how much the processing time is required by your application, and then decide whether to go with it or not. And also for the development, generally all the cloud providers, they provide a versioning concept and for both the deployment and also for development. We can have stage environment or the development environment and the production environment. And also in the production environment, we can keep multiple versions, surveys, servicing the end users. So we have to make use of that and then find out like how exactly we have to use that we have to plan before getting into the development. All the serverless components are supported by CI/CD. In the AWS world, code pipeline, code build, all these support the Lambda applications. Important factor here is security and privacy. Similar to how we develop the application in anywhere, security is always maintained by the user. Here the user is the architect or the programmer. Definitely cloud providers take care of security to a certain extent, but it's users or the architect's responsibility to make it more secure, because every application is different. Some of the ports to be open, etc., to be handled only by the end users. So both to be maintained by the architects, not by the cloud providers. Important consideration here is all the services, cloud services, are sitting on the internet and on the cloud servers that requires internet for accessing that. If you really want to access to test that on your environment, definitely you need internet. In a traditional environment, many programmers, what they do is they'll get the application code and they develop the complete thing on their laptop or the desktop, and then finally they push it to the server in the traditional environment. Here, since it's completely depending on some of the services, it can be PaaS, backend as a service, the PaaS level, they're all sitting on the cloud servers. Internet is a must. So it is difficult to achieve that without internet. Definitely we can emulate that on our local system, provided there is internet. Another aspect is testing. I mentioned that it's completely a distributed level application, and moreover it's a event driven. All event driven, and then the asynchronous distributed applications are really difficult to test. So we have to take care of proper planning before developing the application, like how we are going to test, what is the plan. Another important factor is that there are no comprehensive testing tools or frameworks to support serverless architecture. However, they are evolving now. There are few in the market, but not a very sophisticated testing tools or frameworks compared to the regular applications. We have seen what is serverless architecture, and then there's components, and then how what are the different aspects to be considered for the development. Now the next question is where we can use what kind of applications we can use serverless architecture. Simple example is a static website. Static website is nothing but more of a static content in the website than the dynamic content. That is called as a static website. To give an example, HTML, a website built using HTML, CSS, JavaScript, which serves the content, and then using the JavaScript, to certain extent we serve the dynamic content. That can be easily achieved using the serverless architecture. In this picture, you can see all the static content is served by the S3. All that will be stored in the S3, and then that will be served to the site visitors. It can be on the mobile or on the desktop browsers. Dynamic content is served by the API gateway. Lambda functions are sitting behind the API gateway, and then JavaScript on the pages, HTML pages will call that API and then get the dynamic content served. That is one aspect. And then to give an example on what kind of dynamic content, somebody, an end user, want to download a big file from the system, which is served dynamically which should not be exposed to outside world. For that, what we do in the Lambda function, we generate a signed URL temporarily so that they can download. We'll pass that to the end user JavaScript level and then get that downloaded. Similarly, for uploading also, we generate a signed URL on the S3 using the Lambda API, and then that will be sent to the web client side. Finally, the file will be uploaded to the S3, and once it is done, it will send another request to the API gateway to close that channel. It will invalidate the temporary URL. That's how it works. Next example is a little sophisticated web application. Here, same thing, static website or static content are served by the S3, and then dynamic content is served by API gateway. It also makes use of some of the other cloud services like Cognito, IAM for the authentication level. And in the backend, we can have this content stored in the DynamoDB for some of the visitor related, log related information, and then the RDS for the user related information. And this can also be served using the CDN level. We can push that to CloudFront. That takes care of making it as a CDN available at the different locations across the world so that it will be served very fast. These days, even Amazon Alexa devices, we predominantly use Lambda functions. Even the AWS make it mandate that we have to go through the same channel. We don't have the other choice here. And even the external systems can call these APIs to serve the dynamic content. Another example is the IoT applications. Same thing here, all the IoT related registration of the IoT devices, etc., can be done in the web related component, and then the direct data from the IoT devices can make use of the AWS provided IoT topic and then the rules, and then that the data will be streamlined based on that, and then can be pushed to the DynamoDB through the Lambda functions. One another example is processing the streams. It can be video or the audio streams. We can get the stream here using the Amazon Kinesis, and then the events will get triggered. Lambda will process it, and then finally it will be sent to the DynamoDB and then any other backend service. Similarly, we can even process the images. To give an example, the Facebook, when you upload an image, it will be sitting on the server, and then when the other requests come from the mobile app, the images may be big, so we have to resize the image. For that, we can have this processed in the backend through this mechanism. All the images will be uploaded to the S3 directly using the method we have discussed in the previous slide, and then the Lambda will process it, and then it will call the appropriate AWS or the cloud services, and then get those resized into different sizes so that it can service different mobile or the web or the tablet sizes. So we have seen the certain example like where it can be used. So what are the different pitfalls in implementing the serverless architecture? Main point we hear about everyone who has implemented is the latency or the performance issues only in the initialization phase. All the cloud providers have set their services in such a way that if you do not use a service for a while, they'll take the service or the backend instance of that down for a while. So when you use that for the very first time, when you invoke the Lambda function for the very first time, it takes little time. There is a lag in creating the instance in the backend, and then finally it has to execute your code. So that initial latency causes little bit of performance issue, but AWS has provided another way, that always available method that has to be done in the configuration level. But predominantly, most of the generic function as a service Lambda functions will face this issue, cold start latency. Another pitfall is resource limit. Every cloud provider has got limitations with respect to the services. If you think like you can push 1 million requests to the service Lambda function, no, it is not possible. Every cloud provider has got resource level limitations. One more is short-lived. I have mentioned this earlier itself. When every function Lambda can be Azure function, it cannot exceed certain time. They have got limitations about this. In the AWS world, Lambda has got 15-minute limitation. If the processing time takes more than that, it will be terminated. So execution time should be within this. And all the serverless services are stateless. We have to if the application requires the state to be maintained, we have to do that using our own way. We can push the state to another backend database, something like a SQL or NoSQL database services, or using cache like Redis, etc. One more pitfall, I don't call it as a pitfall. Sometime back it was there, but now there are more tools available, but still we are not to the sophisticated level. Mainly with the monitoring and debugging, it is possible, but it is very difficult compared to the regular applications we do on our servers. It's difficult to replicate in the local environment exactly the same, and even to debug. And IDE support is very limited. Visual Studio and Eclipse have got a certain level of support to serverless applications. And Visual Studio works very good with Azure, since both are from the Microsoft. But Eclipse, yeah, has got certain level of support for implementing the serverless. Another factor is there's no standardization, though there are attempts in making a standard in the serverless world. One such standard is like Knative. It's again by Red Hat, Google, and IBM got together and then pushing for some kind of standard for this. Vendor lock-in is another issue. The moment you implement your application on the serverless level on AWS, it's very difficult to move out from AWS and then push the same set of applications to the Azure or the Google Cloud Platform. It's more lock-in. There are ways of doing it, mainly if you use the standard frameworks while using the serverless components, definitely you can get rid of this lock-in issue. But it requires a lot of effort in terms of implementation. Next slide is busting the myths. There are many myths circled around the serverless architecture. Main point is it doesn't scale well. That's not true. It scales very well. Only thing is initial lag. That is one component. You have to keep that in your mind before going with serverless. And the other factor is there is a limitation on the scale. Both are true. Initial lag will be there, and then there is a limitation, upper limit on the scalable aspect. If you are expecting Facebook kind of application in the serverless, definitely it is not. For that you have to work out with the. We should have some kind of tie-up with the cloud provider. Then only it is possible. And serverless is indefinitely scalable. That's not true, as I explained. There is a limitation on the scalability aspect. It's always a cheap solution. It is very cheap solution when you utilize that serverless components in a minimal level. If you are thinking about 24/7 CPU utilization in a high level, like every second you will have millions of requests coming to your serverless, definitely it's not a cheap solution. But if you're not going with that CPU intensive level 24/7, definitely it's a cheap solution. use PaaS to call it as a serverless architecture. No, it is not true. Both PaaS and BaaS, we have seen that in the first slide itself, both are together called as serverless architecture. PaaS is nothing but serverless. No, PaaS is completely different. We have seen this also in another slide. Serverless is not secure. Of course, it is secure. Cloud providers have taken care all the security aspects to their level, but within the application space, it's architect's responsibility to take care of the security aspects. Serverless is difficult to manage to a certain extent. It is true, but since you do not need to worry about the infrastructure or the backend servers, etc., it's most of the management aspects have gone there itself. It's very easy to manage. Serverless creates a vendor lock-in. Of course, this is true, but there are ways of not to make it as a vendor lock-in by using standard frameworks. So what are the key factors for a successful serverless architecture? You have to analyze before jumping on to implementing the serverless architecture. You have to analyze your application, like what is the load involved, what are the different use cases, what are the CPU time it takes, etc. And then you have to plan like how you can push your existing application or a new application to the serverless world. For an application existing on the data center, in your own data center, there are three ways of moving into the serverless. One is using the leapfrog method. Leapfrog is something like there is an application there. You build whole things, whole replica of that in the cloud, and then one day you go live by discarding it. You jump from this to serverless directly. Another way is organic. Organic is there is an application in the data center. You push the whole thing in a lift and shift approach. You push the same application onto another server. It can be EC2 instance on the AWS or the virtual machine on the Azure. You push the same application on a server on the cloud, and then convert one aspect of the application to a serverless, like that. Continue, and one day you move completely to the serverless world. That is called organic. Strangler is you have got an application on your data center, and then you make one API, and then you call the serverless application one by one. You make it as an API and then call that and then discard. Like that, one by one you move and then discard. So you kill the application on the data center one day. That's called a strangler level of moving the application to the serverless. You have to choose the suitable cloud form. This is most important. Mainly I put this because if you are completely, your developers are completely into the .NET world, definitely Microsoft Azure works very well with it. So you have to really think about like which is better for you, rather than you just go ahead closing your eyes. You have to take care of the cost aspects, how much it costs when you move to the serverless in the cloud platform, and then make a decision. And another factor is you have to continue to use the tools you already know. Developers will get confused because it's a new concept. It requires a lot of thought when you move to the serverless world. So many aspects have to be considered. So always better to go with the tools which developers or the programmers are already familiar with, which can be source code control or the IDE, build and deployment, and also the programming language frameworks used. Another aspect is automate as much as possible. Even creating the serverless components, it's always better to automate the things. Well, for creating the services, you create the scripts for creating the resources, and then also testing, and then CI/CD. In summary, serverless architecture is very good. We have seen what are the different aspects of it. You have to focus only on the business logic, and then our business, we don't need to worry about the backend infrastructure. This cloud provider will take care of all the things very well. It has got auto scaling, all other features, and then release features and innovate faster, because a lot of headache has gone from us with respect to the infrastructure here. Scaling aspects and then the auto scaling and also the high availability aspects are already taken, and it scales tremendously, keeping the cost low. Again, this point only, it is not a very high level environment, high load environment. At the time it scales very well. So finally, it removes all kinds of inefficiencies in terms of scaling aspects. Mainly when we go with the regular data center way, even on the cloud level in a traditional way, for any of our applications, we have the habit of allocating the servers to the maximum level possible, because we are afraid that something will fail. So there is a saying that as for the statistics, people use only 15% of all the servers in a year, compared to the maximum level it can be utilized. So if the server is capable of utilizing for about 100%, we utilize only 15%. So the rest is 85% is unutilized in a traditional environment. In a serverless level, at least that inefficiency has gone. We pay only for the time we use the services. So that way, since the servers are not always running, it's the rest of the time can be utilized by any other user on the same system, by another user in the cloud provider. That way, it's more like a greener computing. Amazon AWS CEO Andy Jassy once in one of the conferences, he has mentioned that if they were Amazon.com were supposed to start today, they would have gone with the serverless architecture completely. That's all we have. If you have any questions, you can type the questions in the window, webinar window. We'll take up the questions for next few minutes.
Great. Thanks, Vijendra. Thanks, everyone, for participation. I see some questions coming in. If there are any questions, please type them in and we'll answer them. We just have, we're already almost out of time, but we'll answer a few questions as we can. Okay, as I'm waiting for some of the questions to come in, there's one question that came in. What's the use or use case of Lambda at Edge? I think I can talk about it. I think Lambda at Edge is a variation of Lambda on AWS, has certain limitations. Not all Lambda functions can be transferred into Lambda Edge, but it allows you to do it. It combines the Lambda functions to the CDN responsibilities that AWS typically does in the CloudFront environment. But essentially, the functions are moved closer to the end users on the edge. Typically, you can use it when the response time or the latency is needed from the request time to serving responses are very critical. You could use that. But larger sense, a lot of those things can be used by how effectively use CDNs and other contents. But if there is a need for a content to be served by the function, but that has to be closer to the end user, you could use that. Other questions? Let me see. I think Vijendra, you could take this. There's a question related, I think a couple of questions, but both of them kind of combine about it. Talk about how to monitor and respond to functions when they're not working properly on the serverless environment, or also how to test the code written on the serverless in a debugging way in a local environment or other. So probably talk about more debugging serverless environments and serverless functions.
Sure, Chala. We did not pay too much of attention on the technical aspects of it because we were targeting more on the business people. Monitoring and debugging is possible. We have got tools in all the cloud service providers. One is the Cloud Watch and the Amazon AWS, where we can see all the logs, whatever happens in the service level. For each service, we can see what are the things happening. We can write any content to the log and then find out like what change it got executed, etc. And also we can execute that using the CLI mode. CLI is command line interface, which we can download on our laptop or the desktop, and then we can debug it in a certain way on the AWS side. Similar to that, even Azure has got the tools.
Okay, so there's another question, probably the last question that we'll take. What are the consequences of serverless architecture as it comes to the operations of the servers or operations people, like either a system admin or a DevOps people? What impact does it have for them, the serverless architecture, whether it is good or bad? Can you talk about it?
Yeah, since most of the operations, system administrator related tasks are already taken care by the service providers. Not much work for the system administrators here with the serverless world, because predominantly 90% of their time in the traditional environment goes towards managing server and then provisioning it, configuring it, and then maintaining it. That is completely gone. Of course, they have to take care another 10% still there to find out anything happens to this and the serverless level components, how to configure these things, and then deployment, and then which instance to be serviced for the end users, etc., can be taken care by the system administrators.
Right. I think that's about the last of the questions we have. We have a few more questions, but we'll answer them via email or something like that. We are almost about 6 minutes over the time allocated. In keeping in respect to everybody's time, like to finish the webinar here. Thanks everyone. Vijendra's and mine contact information is on the screen. You can reach out to us for any questions whatsoever needed. We'll be glad to help or answer and help you in your journey in either in cloud adoption or in serverless architectures that you want to do for your applications or migration, be it new development, whatever that may be. We'll be glad to help. You can reach out to us. Thank you, everyone.
Thanks, everyone. Thanks, everyone. Thanks for your time.